my talk will be about function theory of so-called Cesáro operator. This talk is based on the following my preprint, and the continuous Cesáro operator on the space L2 over the reals has the following form. 1. Sometimes this operator is called also Hardy operator. And the operator, Cesáro operator on the whole real line will be denoted by capital C. And C sub 1 denotes the B restriction of this operator to the space L2 over the unit interval. It was introduced by de Branche in 1961. And in the following, C plus denotes the restriction of C to the L2 on the half line. And both C1 and C plus were studied at Brown, Halmos, and Shields in the seminal paper in 1965. And the continuous Cesáro operator C is a special case of the so-called one-dimensional Hausdorff operator given by the formula 2. If here the kernel, K, if the kernel K in this operator 2 will be denoted by H sub K, is the characteristic, if K is a characteristic function of the unit interval, then this general operator HK turns into the operator C, to the continuous Cesáro operator. And the condition of the boundedness of this operator HK in L2 over R is the following condition. The multiplication K and the modulus to the power minus 1 over 2 should be in L1 over R. And we shall see that the operator HK is not the most general form of Hausdorff operators, even of one-dimensional Hausdorff operators. For example, here we integrate with respect to the Lebesgue measure, and x is multiplied only by u, not by some function of u. But namely, this class of Hausdorff, of one-dimensional Hausdorff operator, is important in the functional theory of the operator C, as we shall see later. The plan of the talk. First of all, I want to describe holomorphic functions of C. Recall that C is the continuous Cesáro operator over the whole real line. Then I'll discuss fractional powers of C and the logarithm of C. If I have time left, I want to discuss functions of C plus. Recall that C plus is the restriction of C to the half line, to the positive half line, and then holomorphic functions of C1. It should be noted that there is a great difference between C and C plus on the one hand and C1 on the other, because C and C plus are normal operators in in corresponding Hilbert spaces, and C1 is not a normal operator. What about the method? The methods of proofs are based on the general theory of multidimensional normal Hausdorff operators, and this theory was developed in the following two papers in Functional Implications 2090 and Forum Mathematical also 2020. First of all, I should note that the spectrum of the continuous Cesáro operator C in L2 of R is the unit shift of the unit circle. And in particular, 0 belongs to this spectrum. The following theorem describes all gives a full description of all holomorphic functions of the continuous Cesáro operator C. The first statement states the following: if F is holomorphic in some neighborhood of the spectrum T plus 1, and F of 0 equals to 0, then there is a unique kernel K such that F of C, in the sense of holomorphic functional calculus, equals to HK, is the Hausdorff operator one-dimensional with the kernel K. Moreover, K satisfies the following three conditions. A, K is concentrated on the non-negative half line. B, the necessary condition for boundedness mentioned above holds. And C, the Mellin transform of the kernel equals to F of 1 over Z zeta, Z, where Z runs over the so-called critical line. And conversely, if some function K meets conditions A, B, and C, where F in C, F is holomorphic in the some neighborhood of the spectrum of our operator C, then F of 0 equals to 0 and 3 holds, and HK equals to F of C. So F of C equals to HK, and conversely, if K satisfies conditions A, B, and C, then HK is a function F of our operator C, where F satisfies the condition small c. The first corollary is the so-called formula of Boyd. Boyd proved this formula for the resolvent of the operator C, for C plus. Here we get the corollary for the whole real line. Our C belongs to Lebesgue space L2 over the whole real line. And in this formula, P alpha is a so-called Hardy operator, or generalized Hardy operator, and Q alpha is a so-called generalized Hobson operator. Let's return to our theorem. Sorry, to our theorem 1. The condition C deals with the Mellin transform of the kernel over the critical line. And so one can suspect that theorem 1 have some connections with the Riemann zeta function. So consider the following example. Sorry. Consider the one-dimensional Hausdorff operator R in L2 over the reals with the kernel K, which is the product of the fractional part of the function 1 over U and the integrator characteristic function of the unit interval. And this example is interesting because here this kernel K satisfies condition A and B of our theorem 1, but condition C is not fulfilled. Moreover, the Mellin transform of this kernel of 1 over Z is equals to the following function 6, where zeta stands for the Riemann zeta. But it is known, this is not old result of Standing and Siriaya, 2020 that Riemann zeta has an essential singularity at the infinity. So the right-hand side in 6 has the essential singularity at 0. And so the Mellin transform of the kernel K in this example is not holomorphic in any neighborhood of the spectrum of the operator C. Now, let's consider the fractional powers of the operator C. Since C is a normal operator in the space L2 of R, then one can apply the so-called Borel functional calculus for normal operators. Let alpha be a complex number with positive real part. So we denote but z to the power alpha, the branch in the right half plane of the complex plane, such that following two conditions hold. In this case, this function z to the power alpha is continuous on the spectrum of our operator. And so there exists a fractional power of C in the sense of Borel functional calculus for normal operators. If we consider the following operator, the so-called Hölder mean of order alpha of the function f, given by the formula 7, then of course H alpha, this Hölder mean, is a Hausdorff operator of the form Hk. This operator is bounded for all alpha with positive real part, and the following theorem too holds. The fractional powers of C equals to H alpha. So fractional powers of C, C to the power alpha with positive real part, and all Hölder's operators with positive real part of alpha coincide, which formula 8 gives. And of course, one can imply the Borel functional calculus in this case, and the so-called spectral mapping theorem for the Borel functional calculus gives us an opportunity to compute the spectrum of Hölder, means Hölder operator. This is the image of the shifted unit circle with respect to this branch of the function z to the power alpha, which formula 9 gives. This is first corollary. Then one can compute the norm of the Hölder operator in our case. In particular, if alpha is real and positive, then the norm equals to 2 to the power alpha. Next, we have the following property of the Hölder operator. If H alpha to the power beta equals to H alpha beta, this is a corollary 2, and the corollary 3 states that this operator H alpha form a holomorphic semigroup in the right half plane. We consider this semigroup operators with respect to alpha. If alpha runs over the right half plane, we get corollary 3 states the holomorphic semigroup of operators. So it is natural to denote by the logarithm of C the generator of this semigroup of operators. It should be noted that logarithm is not bounded on the spectrum of C because 0 belongs to the spectrum of C. But, and therefore, our definition 10 is not the special case of the Borel functional calculus of normal operators, because Borel functional calculus of normal operator deals only with bounded functions on the spectrum. And here we get an unbounded function on the spectrum, but we do denote the logarithm of C as the generator of this holomorphic semigroup C to the power alpha. I want to describe the spectrum and the inverse of the logarithm. And I need the following well-known special functions, nu of y minus 1, given by formula 11. And in terms of this special function, first of all, we can describe the resolvent of the logarithm. The resolvent of the logarithm is given by the formula 12, and we see that the resolvent of the logarithm is also the Hausdorff operator of the form hk. And the spectrum of the resolvent is given by formula 13. This is some curve, and the theorem 3 gives us an opportunity to describe the spectrum of the logarithm. The spectrum of the logarithm theorem 4 states that the spectrum of the logarithm is the following curve, given by formula 14. And note that 0 do not belong to the spectrum of the logarithm. So the logarithm has a bounded inverse. This inverse is given by the formula 5. So we see that the inverse of the logarithm of C is also a Hausdorff operator of the form 15. And now I should to speak about the C plus. For an arbitrary operator A in the space L2 over the R, we denote by A plus the restriction of A to the subspace L2 over the R plus, over the non-negative reals. And so C plus is a restriction of C to this space. Lemma 1 gives us an opportunity to reduce the study of holomorphic functions of C plus to the study of holomorphic functions of C. So lemma 1 shows that these two operations, the restriction to L2 on R plus and the taking of holomorphic function commute. And so theorem 1 and lemma 1 imply the following full description of holomorphic functions of C plus. This lemma is similar, of course, the theorem 6 is, of course, similar to the theorem 1 and gives the full description of functions of C plus, of holomorphic functions of C plus. And similarly, theorem 7 gives the full description of fractional powers of C plus, because formula 18, this theorem 7, states that the restriction to R plus and the taking fractional powers also commute. It should be noted that formula 11 for the positive alpha last year appeared in the paper of Delgado, Leonard, and Civic in Journal Mathematical Analysis and Applications as a definition of the fractional powers of C plus. And to suggest that this definition is correct, to justify this definition, Delgado, Leonard, and Civic in their paper proved the semigroup property of this operator defined by the formula 11. Of course, in our approach, this is obvious, since this is a real fractional power. This fractional power, of course, satisfies the semigroup property. And as regards the logarithm, of course, formula 19 shows that the operators of restriction of C to the R plus and taking logarithm also commute. And now let's consider the operator C1. Recall that C1 is the B, so-called B restriction of C to the interval 0, 1. This means that we consider our continuous Cesáro operator C only on the space L2 of 0, 1, and the argument also runs over the interval 0, 1. And also these two operators are operations, the B restriction and taking of holomorphic functions commute as lemma 2 states. Of course, since these two operations commute, one can apply our theorem 1 and to get the full description of the holomorphic functions of C1. Theorem 8 states that if F, sorry, this F is not correct. If F is a holomorphic, it should be noted that not only the difference between C plus on the one hand and C1 on the other is that C and C plus are normal operators in L2, and C1 is not normal. But it should be noted that the spectrum of C1 is a shift of the unit disk, not the shift of the unit circle, but shift of the unit disk. And of course, if we want to apply the holomorphic functional calculus to C1, we should consider a holomorphic function in the neighborhood of the shift of the unit disk, d plus 1. And then we get the following theorem. If F is holomorphic in some neighborhood of the spectrum of C1, and if of 0 equals to 0, then there is such kernel K that holomorphic function F of C1 is the B restriction of HK, and conditions A, B, and C hold. Conversely, if a function K meets the conditions N, B, and C, and in the condition C, F is holomorphic in some neighborhood of the spectrum of operator C1, in some neighborhood of the shifted disk, of the shifted unit disk, then F of 0 equals to 0. So this condition, F of 0 equals to 0, is necessary. And we get the same fact that the B restriction of HK is the holomorphic function F of C1. And here I want to discuss some bibliography. The first item here is the paper of the branch, 1961, where in particular, the operator C1 was introduced. The second is the seminal paper of Brown, Halmos, and shields, where C1 and C plus were studied in the spaces correspondingly L2 over the unit interval and L2 over the half positive axis. And this is my preprint. The 13th item is the это обзор, the survey on the Harmonic operators in the first 2 decades of our century. 5 and 6 is my papers on the general theory of normal Harmonic operators multidimensional in L2 over the R to the power n. Thank you for your attention.